Good afternoon, everybody. Thank you for registering for Milling Tools, the Forgotten Step in Your Digital Workflow webinar hosted this afternoon by Dr. Marilyn Go. Dr. Marilyn is the Head of Research and Innovations with Prima Digital. She is the world's foremost leading expert in the field of carbide and tooling design. Dr. Marilyn has a PhD in the application of artificial intelligence in manufacturing control. She has over 15 years of experience working with internationally recognized companies, including Sandvik, Airbus, and leading universities. Dr. Marilyn is published in over 12 international papers and is the principal inventor of 3 patents on cutting tools. And with that, I pass the webinar over to Dr. Marilyn Go.
Thank you. Thank you, everybody, for joining the webinar this afternoon, especially taking your time out from a very busy schedule. To start with, I would like to draw attention to this abbreviation that you will see throughout the presentation. If I use the name tool C, it means this tool is made by manufacturer C, and so on and so forth. Now then, the aim of the webinar is so that I can share with you some of the thought on how quality milling tools could help you optimize your workflow. Now, it's not just optimizing your workflow, it also, if it's something that we do not consider carefully, it could cost you downtime and also cost. And of course, today we are only focusing on roller mill milling zirconia only. Now, when we talk about quality tools, what does it mean? What sort of characteristic should we expect from a quality milling tool? Now, how can this quality milling tool possess such characteristic then? At the end of the day, what does it mean to you as an end user to have a quality milling tool? This is the workflow that we are familiar with. We just take an example, as in a patient coming to the dentist looking for a crown, and we use an example of a zirconia crown because we are focusing on zirconia in this case. And the dentist will prepare a tooth that requires a crown for, and then perform a scan, and then send that scan image or file to the lab that design a crown for the patient. Now in here, the software that is used to design is called the CAD software, and the software that is used to nest and then send it to the milling machine is called the CAM software, where the dental technician can then nest the design onto a zirconia disc. We are using an example here, the zirconia, and then it will send the CAM software will generate the program that will drive the milling machine. In here we use a roller machine as an example, and for zirconia, there are some sort of post-milling treatment or operation that is required. Now, one of them being the sintering process, where the zirconia will need to be sintered so that it can reach the full hardness and the toughness that's required as a finished product. Then the crown will be sent to the dentist to be put on to the patient. Now then, in this workflow, normally when we choose a mill, we will decide, oh, should I buy a roller mill or should I buy a VHF mill, and so on and so forth. But when it comes to a milling tool, do we put much thought, or do we actually think more than just say, oh, you know what, any tool will do the job, or maybe I just get an expensive tool, it could do the job as well. But does it mean a quality tool an expensive tool, or is a quality tool any tool? What do you think? Now we'll explore this question throughout the presentation. The first thing that I would like to share with you is what sort of characteristics should we expect from quality milling tools? At least, I would say, at least three of this. At least 3 of this. Now, the first one would be a milling tool. A quality milling tool should give us a precise cut. It means that there will be less adjustment that's required after milling, and the tool should last long. Now you'll be asking, what do you mean by last long? Comparing to what? Now I'll say at least compared to common tools that's in the marketplace, which can mill any materials. Some of the tools that says, I can mill, you can use this tool to mill wax, PMMA, zirconia, anything. At least compared to this tool, a good quality zirconia tool should last longer than this tool. But at the end of the day, what you require is a lower cost per restoration because it lasts longer. Now the last point is that a quality tool should be kind to a milling machine. Now this is quite subtle. I'll explain later on now, because when it's kind to a milling machine, you would have less downtime. The first point first, precise cut. Now we have done a study with the university. Of course, we did the milling test in-house, and then we sent the result to this university in London to perform the analysis. What we have done is that we have milled a series of crowns using a Prima tool, and also using a tool made by A and also B respectively. And the aim of that test is to find out which of the crowns being milled are more accurate or accurate as compared to the digital model. Now I actually took the digital model from the sample STL file that comes with the mill box. That was mill box 2017, and the test was done using uncoated tools. So we use 52 DC machine and mill box, and now we mill this full contour crown, as you can see in the image here. And for each of the disc, I managed to nest 14 crowns within the disc. Here is the cutting condition. So this is what people always talk about milling strategy. So the key point in here is that I did not change any cutting condition that comes with mill box that was used for ZCB2, which is the original tool that when I bought the machine, this tool came with the machine, which is the original Roland tool made in Japan. So I was using the default cutting condition in here. And then when we are doing a test, we need to decide when to stop. Yeah, so so you're doing a series of tests, there must be a stopping point. So the stopping point was that when I found at least 3 or more crowns within a disc that has chipped margin, I stopped the test. So when you look into the next image here, you can see these 14 crowns in this disc, and I put an arrow, the green arrows, you can see those are the crowns that chip. So when I've counted 3 more, I stop the test. Then I send all these crowns to be analyzed by the university, and what they did is they analyzed the outer surface and also the inner surface. I'll show you later on. Now, the measurement was on the volume deviation. Now, you look into the 4 pictures here. By our naked eyes, we are not able to measure volume. With our naked eyes, we cannot measure. So what we did is that we measured it, we scanned it, and we perform a measurement using a software. So if you can see, this is what the table shows. So from the left, let's read from the left. If you look at Prima, it's a disc 1, Prima disc 4, and Prima disc 9. That is referring to, with Prima tool, we are able to mill altogether 9 discs. So if we quickly do our calculation, 9 discs, each disc consists of 14 crowns. That will give us 126 crowns. If you got it right, well done. Now, for 2A and 2B respectively, they can mill 7 discs altogether. So that gives 98 crowns. So this is the number that you see a lot in our brochure, the 29% increase in tool life. This is how we get the numbers. Now we move to the right of the table. You can see 0.01. I highlighted the number, 0.01. That is in volume deviation. So that tells us from this one, for Prima, this 1 to this 9, the volume deviation is 0.01. That's very small as compared to other two. Now this is the outer surface. What about the inner surface? These are the images showing the inner surface. Now these images are giving us some sort of image, some sort of picture, so that we know what is being analyzed. Now, it's not for us to quantify. Yeah? We need to be able to measure to quantify. And therefore, we do a measurement. And these are the results. So if you look 0.3, that is the volume deviation again. So that is for prima 2 from this 1 to this 9. Now, compared to the other numbers, you can see there 1.2 for the volume deviation for 2A and 1.67 the volume deviation for 2B. Now, if again we quickly do our maths, that is 4 times better. That is just about more than 5 times better. Now, this inner surface is very important because we know that is where the fit is. So at the end of the day, what does this tell you? So what does this mean to you then? Now at the end, it means with the quality tool, we are able to mill closest to the dimension that we define it. Therefore, there will be less milling adjustment after milling. Okay, so that is what we have covered. The first point, precise cut. The next point we want to cover is the tool should last long. Okay, so that when it lasts longer, it means ultimately the cost per restoration is lower for you, and there's less setup for tool. Now, this is one of the quote I got from our customer. They said they like our tool very much, especially there are 3 points there he mentioned: surface finish, vibration, and also, again, he says lasting much longer. Now, for today, we only focus on the last long because we haven't got the time to cover the other 2 points. Now, in order to explain to you why this tool lasts long, we see, I show you a result that we've done an internal test in here that we carry out using tool made by Prima and tool made by A and B respectively. Now this time is with the coated tools, Now the aim of the test is to see or to determine the number of good restorations that these tools could mill before the poor restorations are found. Now again, the stopping criteria is the same as the one that we've set for the previous test. The machine that we're using is the same. Mill box is used. Cutting condition is the same, exactly the same. Now this is the result that we get. Now with the Prima tool, we were able to mill 33% more as compared to 2A. Now if you remember correctly, we have another tool which we have tested, that is tool made by B, but it's not in here. So where's the result then? So the result, I would say I did not put it down in the graph because I think it should come out from the graph. I'll explain to you later with this point here. Now our tool, a quality tool, should be kind to a milling machine, so that will actually give you less downtime. Now we come back to this 2B. Why is it not on the chart? Because this is what happened. I call it premature failure because a coated tool should last longer than 25 or 28 or 56 restorations. This is what I found after milling a 2 separate tests, 2 sets of tools. After milling this number of restoration, it starts chipping. Now, really, I don't want to use chip tool on my machine. I really don't want to do that because it will increase the spindle load, and in the long term, it may damage my spindle. Now, if you read the instruction from a Roland, it says spindle life is 2,000 hours. And sometimes you may wonder, you've changed your spindle, you have calibrated a machine. Sometimes, you still doesn't mill right. Yeah, maybe you have this line across your restoration. You wonder why. Maybe it's a tool that you didn't see. But because this chip you cannot see with your naked eyes, I'll show you how big is the chip later on. Now, how could good milling tools possess such characteristics? Now we've identified these are the characteristics, good characteristics that we wanted to see on tool. Yeah. Now how can tool possess this then? a few things, at least two substrate, two geometry, coating. Now this is only on coated tools, and manufacturing process. Now for the uncoated tools, we use good carbide and hard carbide. Now do we know why hardness? Because hardness is one of the key material property for wear resistance. So if we wanted to have wear resistance, it has to be hard. Now for coated tools, it's slightly different because if we are putting coating on top of the tool, then the coating must be harder than the carbide. Yeah. The other thing is that the coating must be, not can be, but must be compatible to diamond coating. Now I mentioned diamond coating because a lot of tools in the marketplace today for zirconia is diamond coating. Now we can't just put any diamond coating or use any carbide. It must be compatible. Otherwise, this is what we see chip. Now this is not the only factor, but this is one of the factors causes the tooth chip, because the diamond and the carbide are not good friends. The next thing is the geometry. Now sometimes we hear, one tool can do all job. Yeah, it's not really optimal because different material deform differently when it's being cut. So when the material deform differently, how could you use one tool for all materials? So that is questionable, really. So what is good geometry then? Now, good geometry is a geometry that allows you to cut with less or low cutting resistance. Now, how do we measure cutting resistance? Now, cutting resistance we cannot feel it. Yeah, we don't feel it. We measure it. How do we measure it? Cutting forces. Now we send these tools out to be measured in a technical university, engineering university. So they did this measurement for us. Again, it's blind to them. They do not know which one is Prima tool, which one they know is a 3-foot tool. Of course, they don't know. We make the tool, and we also got a tool that is in the marketplace, the tool made by A, which is a very common tool, 2-foot tool. Now less resistance means less force, lower force. So what you can see on the right, the chart, the graph is telling us that the Prima patent pending tool are actually having or generating the lower cutting force about 50% lower as compared to the other two. Now, what is Newton here? 0.43 Newton. Give you an idea. It's about 43 gram force. Yeah. The next thing is the coating. Now, in terms of coating, of course, we know if we are putting a coating on top of a tool, the coating must be harder than the carbide. Otherwise, there's no point. So if we think about hardness, we think about diamond because that is the hardest thing in the world, right? So in this case, we are using a diamond coating. There's man-made diamond coating using a chemical vapor deposition method, and the hardness can go up to the hardness of the natural diamond. It's kind of amazing on this. So when we look at under SEM, we are talking about nanoscales, microns nanoscales here. Yeah, we'll look under SEM. This is how you see a diamond coating. So on the right, you can see crystal of diamond. On the left, it's very hard to see. Now, come back to this question. Is an expensive tool a quality tool? What do you think? I give you 2 examples. So there are 2 tools here. One on the left costs you about 150 USD. The other one on the right costs you about 60 USD. Now, the expensive one make about 56 restorations, and the cheap is bigger than the cheaper tool that make more than 100 restorations. And the chip size is smaller yet. It's yet smaller. So I call it premature. They actually fail prematurely because a coated tool should last much longer than this. If it's a diamond coating, it should be much longer. The last point here is on manufacturing. And of course, there is ISO standard. I'm not sure whether you know. Tool maker need to conform to this ISO standard in terms of shank diameter and also in terms of head diameter. So we do conform to these tolerances. Now, I just show you a video. This is our manufacturing plan. so that you can see. Sorry. We use rollomatic machine, very highly precise machine, good quality carbide. And we also perform checking, in-process checking every time when we make our tools to make sure that it's of good quality. So ultimately, what does it mean to you? Ultimately, a quality tool should allow you to cut precisely, should last longer, and should be kind to your milling machine, really. So when we talk about milling tools, it is an important step in your workflow. So rather than using, you know what, any tool, but use quality tool. Save you time, save you cost, something to think about. So if you like to contact us, here is the email address. I'm happy for you to contact me if you want to know more about tools, about carbide, or about coating. Now, one thing to point out to yourself, we are based in the UK and we design and manufacture in the UK. Thank you very much. Any question?
Okay, Dr. Gull, it looks like there's no questions from the audience. Thank you so much for your time this afternoon for presenting this topic.
Thank you very much.
Thank you, everyone. Have a great afternoon.